Sec, I gotta go grab my notes for 4.1.
All right, so let's start our review here. So I'm just gonna go over a few main topics kind of in order of the way we covered them. The first big topic in the final review here are lines. So that's what we're gonna start with. So a couple things to remember about lines. So lines have a slope. And I think that's the most important thing about lines in terms of using them outside in the real world and working with them in analysis and graphing. Slope viewed graphically is a rise over a run. Rise is a vertical change. And run is a horizontal change. And change, usually we measure change by subtracting two things to see how they've changed. And that's our y2 minus y1. That'd be our vertical change, two different y values. x2 minus x1 would be our horizontal change. And remember, the slope also has another name. It's called the rate of change. And remember, the change is our subtraction, which we do top and bottom, and the rate is the division. So slope, again, is also known as rate of change. We have this rate here. We're dividing these two differences, these two changes. And then just a rough graphical version of this. So that's my y-axis and my x-axis. And I have a couple of points, and let's pick that as one point. And let's say that's the other point there. So this would be my first point. X1 is the x value, y1 is the y value. And then we've got this other point. We'll make that a different color. How about red? And then that second point, we just call it the second x value. And there's some second y value to go with it. And then remember, it doesn't matter which point we call the first or the second point, we can go either way. But in this case, my rise here would be a drop. That's a little better. And then my run. And that just describes how to get from one point to any other point. And two of those together give me my slope. Some other things about slope. In this case, the line going through these drops down from left to right. So slopes are positive, negative, or zero. So if, like in this case, if you end up with a negative slope, which is what we would have here, visually, with a negative slope, we see a drop from left to right. And if we had a positive slope, so we did our calculation, ended up with a positive number, then we would rise from left to right, or increase from left to right. So those are the big ideas about slope. And then often the equation we use for the line along with the slope, so kind of our standard equation, would be that y equals m, the slope, times x plus b. This is also called the slope-intercept equation. And remember that value b has a couple ways to refer to it, just like we call slope or rate of change. The b is sometimes called the y-intercept. It's where we start on the y-axis. And sometimes referred to as the starting point or initial value. And a lot of the problems we dealt with, our x-axis was often time, and time 0 was just the time to start at and then look to see what happens after that. Sometimes it was a year, right? Like time 0 was the year 2000 or 2010. And then we counted years after that, for example. Or time that we intake some coffee, and then we look at how much caffeine is still left after that initial time, and what was the initial value of the caffeine. And as far as the y-intercept, it's a point, right? It's the point 0, whatever that number b is. In the beginning of the lesson, there's a bunch of problems that just kind of remind us about what these different pieces of the line mean and how they relate to the graph. We'll do those practice problems in just a minute. I want to talk over 2 other main topics. So that's main abstract ideas about lines. Second big idea we looked at, part 2, abstractly would be called exponential equations. And there where we looked at, instead of a rate of change as a fraction, we had a percent change. And that percent change was an increase or a decrease. And that percent change was usually given the letter R. Examples of R would be like annual percentage rate. We looked at depreciation rates for like a car. And a bunch of others. We'll see some examples of that in the lesson in the homework. And the formula that we ended up using for these exponential equations, the main one was we had some new amount we were calculating based on some present amount times 1 plus r to the power t. So the big thing about exponential equations is you have a variable as the exponent. That's kind of a key indicator in an equation if you have an exponential equation. And so just back to some examples of the exponential equation, if we looked at the annual percentage rate idea, this could be an investment. Where we have our new amount, maybe we started investing $500 at 2%. So we'd have 1 plus 2% as a decimal to the power t. And that cleans up a little bit. We can add the 1 and the 0.02. So we could simplify this a little bit by saying A equals 500 times 1.02 to the power t. Another example we looked at was the depreciation of a car. And there, maybe it was a $20,000 car. and we were losing, say, 15%. So then our R would be negative, so that would be a 1 minus. So this could be a car starting at $20,000, losing 15% per year. And we can do the subtraction inside the parentheses here, so we could simplify this a little bit and say it's A is $20,000, 20,000 times 1 minus 0.15. We take 15% off, that leaves us 85%. As a decimal, that would be 0.85 to the power t. So that's another example. Now, not everything fit this pattern here. Sometimes they looked a little bit different, like the half-life. So we'll come back to the half-life later. But coffee was another example of depreciation. My recollection is it's about 10% per hour. Is that right? Calculate that. I should have thought about that ahead of time. Yeah, 10 or 11%. So coffee kind of fit into this here, with the caffeine. For the amount of caffeine, maybe we started with 100 milligrams, and let's say it drops about 10% per hour, then we would have that 100 milligrams times 0.9, we lose 10%, we keep 90%. So this is a rough estimation of how caffeine affects some people. Caffeine wears off over time. And then graphically with problems like this, one of two things happens in the graphs that we've seen so far. With the investment type problem, those graphs, that was very sloppy, let's try that again. The graph for some kind of investment, generally it starts off slow, but then all of a sudden it just kind of takes off fast later. So in my young years for my retirement account, it doesn't look like it's doing much, but then all of a sudden, right before I'm ready to retire, all of a sudden it starts really gaining the amount of interest. Depreciation is similar, but backwards of that. Let's do green on that one. So with depreciation, instead of or something rising up, we drop down the other way. So depreciation would start somewhere and it would drop fast at first, but then kind of slow down as it drops. And coffee does kind of same thing. So these both have kind of a similar graph if you were to plot a whole bunch of points. All right, one more topic, and then we'll actually do stuff together. So this is kind of like helping toward the notes we need to accumulate. Part 3 we've been working on for the last couple of weeks, and that's other powers and roots. So the simple versions of these, and then I'll give some examples, would be like y equals x squared. We call that a quadratic equation. And then to solve a quadratic equation, we needed square roots. And just a reminder about that, if 3 squared is equal to 9, then the square root of 9 is equal to 3. And so we're trying to get used to that idea there, how those square roots can be helpful in solving these equations with squares. And then we took it a step further and we looked at, say, third powers. And I don't remember naming these, but these are often called cubic equations, as in a cube. And then we needed a cube root to solve these. So if I had, say, 2 to the third power is equal to 8, then the cube root of 8 would be equal to 2. And examples of these that we played around with a little bit, there was the distance versus speed, braking distance versus speed. Ended up having a square of the speed. Anytime we deal with area, we have squares to play with. Would be another example there. And for the cubic equation, the problems we looked at there mainly were about volume. Like for a sphere ball, if we know the radius, then the volume of a ball is 4/3 pi r cubed. And one thing I just realized I forgot to mention with the exponents was logarithms, right? Just like we need roots to solve squares or cubes, we need logarithms to solve these here. So just put a little note in there. So we use log when we try to solve for variable exponent. And we were getting pretty good at that before we moved on to the roots. So that's kind of overview of the main ideas we did all quarter, summed up in 10 minutes.